So this is the traditional part. I've got about 15 minutes worth of material here, where I'm going to try and talk to you about some of the more recent work in our research group. And the title of the talk is called the Single Fiber Endoscope. I will say a few more words about what I mean by that shortly. And it is part of the UK Quantum Technology Hub Network. So it's funded through Quantic, and as I said, part of the UK National Quantum Technologies Programme. And I noticed that David Delpy was there on the participant list. So I hope he acknowledges that I've acknowledged the hub funding correctly. Right. So single fiber endoscope. What I'm going to show here is that by using advanced beam shaping techniques and photon timing, we can make an endoscope the width of a single human hair. And down the length of that human hair, we can do 3D imaging. So just to cut to the end of the talk, I always believe in starting off a result. This is a video taken with our single fiber endoscope. You see that it's sort of vaguely video rate. It ranges up to about 3 meters. So this is Peter sitting in the lab waving at the endoscope. And let's just remind ourselves that this fiber, this single fiber, has a 50 micron core and about 120 micron diameter cladding. And the top picture we see is the intensity of what we see. And the bottom picture, the color-coded image, is essentially the depth of what we can see above. And from that, we can see that we've got a depth resolution of about 1 centimeter or so. So what I'm going to talk about now is how we set about doing that. So it isn't imaging through a fiber. Let me just say that first of all. What we actually do is create a scanning spot at the distal end of the fiber. And so what we do is we shine a laser beam into one end of the fiber. And what we want to get out of the other end is a scanning spot, and such like I've shown on the left there. But unfortunately, when we shine light into the optical fiber, light couples into different modes. All those modes propagate along the fiber with a different mode index, with a different speed. And so what you end up getting out the end of the fiber is essentially random interference. You get something that looks like a speckle. No matter what you shine into the fiber, what you get out the other end is a speckle pattern. And what we need to do is find a way of controlling that random interference to create not speckle pattern, but back what we wanted, back a spot. And in doing so, I'm going to say that we're going to represent the fiber by some kind of matrix transform. So it maps pixels on the input to pixels on the output. We are going to understand that transmission matrix. And then what we're going to do is, rather than shining a spot of light into the fiber and getting out a mess, we're going to shine into the fiber something that looks like a mess and hopefully get out a spot. And I'm going to talk about this within the context of optical fibers, but clearly any complicated transmission system could be analyzed in the same way in terms of matrices. So who's doing what? Well, so most of the work I'm going to talk about is actually being performed in the laboratory with Dan Stellinger, and you can see his picture there on the top left. Other people involved, David Phillips at Exeter, Peter also at Glasgow, more about him in a second, and most importantly, Thomas Tischmar in the Czech Republic. And basically, and I'll come back to this now talking about the future, I've known Thomas. Thomas and I have known each other for many, many years. He was in St Andrews at one point and then at Dundee. And we realized that each of us, or each of our groups, was doing something that was of interest to the other person. He knew how to make endoscopes out of single fibers, and my group knew how to shape beams very, very quickly. And since the key to these endoscopes is shaping beams, clearly there was something we could learn from each other. And so that, as so often throughout my career, you partner up with another research group because they know something that you'd like to know. And importantly, you know something that they'd like to know. And so it becomes an effective match. So let's go back again and think about the endoscope problem. Traditionally, endoscopes are made not from a single fiber, but from a bundle of fibers, where every fiber in the endoscope corresponds to one pixel in the image. So if I want an image with 50,000 pixels in it, I need to bundle together 50,000 optical fibers. Consequently, the end result of that is you end up developing something which is a few millimeters at least in diameter. Now, given that I just said that these fibers, 50 micron core, that would be a multi-mode fiber. And depending on the wavelength, that might support something like 1,600 to 2,000 separate fiber modes. You can see that the information capacity of the fiber should be sufficient that I could shine through the fiber a 2,000 pixel image. And as I've already said, the problem is, unfortunately, that the modes all coupled into each other propagate with different speeds. And so what comes out the end of your fiber is essentially an interference mess. Now, I mentioned already that Thomas was, I think, leads the world basically in use of single fiber endoscopes. And there's a couple of papers that I've put up from him, Seeing Through Chaos in Multimode Fibers, Exploiting Multimode Waveguides for Pure Fiber-Based Imaging. And then I mentioned already that there was an area where we realized that we each had something to learn from each other, namely the high-speed shaping and controlling the intensity, phase, and polarization of beams, in this case, using a digital micromirror device work that we did together. And that's going to be the link between our areas of expertise. So this is just the same problem that I've already outlined, but now in pictures. And we've got this nominal input, which is a scanning laser spot focused onto the input facet of the fiber. And that information, unfortunately, is essentially scrambled. And at the output, I get something that looks like a speckle pattern. I move the spot around and I get out a different speckle pattern for every spot position. So instead of doing it pictorially, let's now represent that problem or that system mathematically. We're going to do so through matrices. On the far right-hand side at the top here, I've got the input to my optical fiber, and each I1, I2, I3 is an independent pixel. It was a round image, but it's been reformatted into a column vector. And I've already given us the idea that roughly speaking, there's going to be 1,600 different positions of the spot. Then on the output, there is the same mapping. Here are the positions on the output. But unfortunately, the fiber, if this was just a diagonal matrix in the middle here, then every pixel at the input would be mapped perfectly onto every pixel at the output. But it's not a diagonal matrix. It's a populated matrix with complex numbers because it's not just intensity, it's phase that we're mapping along. And so the output of the fiber is equal to the input multiplied by the transmission matrix. Now, I multiply both sides by the inverse of the transmission matrix, and lo and behold, it allows me to calculate what is the input I need if I have a particular output in mind. And so if I want to create a single spot at the output, represented in this vector O, I multiply that by the inverse of the transmission matrix, and that gives me the input shape that I need to create. And I'm not going to go into much details. I'm sure many of you can work out how we do that. We do that by basically using a spatial light modulator. That spatial light modulator essentially is a pixelated device, either liquid crystal or micromirror, where I can create effectively a diffraction grating. And by designing the diffraction grating or designing the hologram appropriately, then I can create any complex light field I choose to make. And so now, this is what we had before. I've got them both up there, the problem. We've got the input, and it has given me a random output. But what I want to do is shape the input beam so that I get a scanning spot output. And so that is basically how we are doing it. That's, again, a nice photograph taken by one of our PhD students, Kevin Mitchell, now Dr. Kevin Mitchell, of a laser beam being shone into a multimode fiber, and we get out a mess. We then shape the beam and we get out a spot. We can get about 50% of the energy, the total energy of light into that spot. And then by changing the pattern at the input, we can make that spot scan around. And actually, this scan rate here is about 2 or 3 seconds per frame. We can scan the spot using the digital micromirror Texas Instrument type device at about 20,000 spot positions every second, which corresponds to a frame rate of about 7 Hertz. Now, we don't just scan the beam. What we do is we use a pulsed laser, and then as well as measuring how much light comes back, we do a time analysis of when the light comes back, and that time, just like a bat, gives us the range of each individual pixel. And so this is essentially a nice little schematic here of what the system looks like. We've got laser, this device here that looks a little bit like a chessboard. That's the digital micromirror. So that's essentially the working components from a data projector, where we're setting it up to look like a diffraction grating, but the diffraction grating lines are all wiggly such that the first order diffracted beam takes on the intensity and phase structure that we so want. We project that intensity and phase structure into the fiber. We generate a scanning spot. And then in our case, we have a second fiber, which measures the backscattered light. So we've got an illumination fiber, which is 50 microns in diameter. And I have to be honest, we pushed the boat out a little bit in our back fiber, in that our backscattered return fiber is 500 microns in diameter to get more photons back in. We go in with a Q switch laser. It's one of those little lasers, cost about 7K, generates about pulses, nanosecond pulses at 20 kilohertz. Our total output power is of the order of a milliwatt or so, and then that milliwatt forms a scanning spot. We get backscattered light, it comes back along the return fiber, and we digitize it at about 1 gigahertz. We're using an avalanche photodiode as the detector. That is the schematic there. That is the real thing. So it looks pretty much as I described it to you. The outgoing fiber is orange, the return fiber is red. And let's have a look at some more videos. So here we see a mannequin head. It's a little plastic dinosaur in the foreground. And then we have a carrot on the end of a string, not really a carrot, just looks like a carrot, as a pendulum, just to give us some idea of the frame rate that we can cope with. And you see the image above is essentially the backscattered intensity, and the image below is the time of the backscatter peak, giving us the depth, in this case, going from a depth of the dinosaur, which is about 45 centimeters away from the distal end, up to the sort of ears of the mannequin, which are about 70 centimeters away from the distal end. You've seen this video already, but just let's say again, so now a bit more detail. We've got a 20 kilohertz laser. We're using 1 pulse of the laser per pixel of the image. The average power going out of the laser is about the end of the fiber is about 1 milliwatts. 50% of that energy we get into the correct spot, and the backscatter collection is through a second fiber, 500 microns in diameter. Just to show we can push the boat out a little bit, this is actually imaging the inside of the lab. This is imaging about a 5-meter range. You can see an intensity image in the middle, and then the depth image on the right-hand side. So this is pretty much where we are. We've got a current frame rate of 5 Hertz, 7 Hertz, something of that order. We've got a lateral resolution of about 40 by 40. That 1600 corresponds to the number of fiber modes in that size of fiber. If we wanted a higher resolution image, we'd have to use a larger diameter fiber. The depth resolution is about 5 millimeters, and we'd like to move that up. I think we want a bit more resolution, so we're looking to get up to about 100 by 100. That will be a 100 micron core fiber. And we can do imaging up to about 4 meters. At the moment, we're imaging down about 30 centimeters of fiber. We'd like to go higher than that. We'd like to go up to 5 meters. And this is now the crunch point, which I haven't spoken about. All of this is only possible because we know the transmission matrix of the fiber. We have to measure that transmission matrix by shining down the fiber known spots and recording the known patterns, and learning the recipe takes us about 35 minutes of measurements, which is great as long as you don't move the fiber or heat the fiber or bend the fiber. If you do that, as things currently stand, you have to relearn it. But we don't think you do. We think we can extrapolate from one setting to the other. Let us see. And then at the moment, we're using light at 532. We'd like to move that into 1064. And so I've mentioned already, of course, Thomas and the wonderful collaboration we have with him. More currently, we've been working with Harriet Watt, looking at these transmission matrices. How might we use machine learning techniques to learn how to modify the transmission matrix when the fiber is subject to bending or heating? And rather than looking what comes out of the fiber to do that calibration, maybe instead we can measure what's backscattered out towards the source. And then other things that we need to optimize. So that's pretty much where we are with our system. That is pretty much the first part of my talk concluded. And now we're moving into what the seminar was meant to be about. Now going to talk about the future, not the future in relation to this particular experiment, but the future more generally. And so I was chatting about this with Akil yesterday, and we were talking about crystal balls and how I don't like them. I mean, we've all had that experience, whether it be at a research council or a departmental meeting, where somebody goes, what research are you going to be doing in 10 years' time? And the honest answer is, I don't know. I hope I'm still doing research in 10 years' time. I hope it's creative. I hope it's imaginative. But nevertheless, we always participate in these functions and we come up with a list of hot topics. And then I challenge you, when you look at the list of hot topics, to work out who was sitting in the room. Because my experience of these things, including the times when I've been involved myself, is I don't quite know what crystal ball that they were using, but the crystal ball must have been quite reflective, because what they ended up seeing was themselves. And the future looks like what I'm doing now, but a bit better. And clearly that very rarely is the right answer, even for the individuals concerned. And so for a moment, I want to dispense with the crystal ball. Having said that, my last slide, I have fallen into the trap and I have made a prediction. But in the interim, let us not do that at the moment, and ask instead to think about, where do your ideas come from? What were you doing the last time you had a research idea, the idea for your last grant application, fellowship application, honours project? What were you doing to get that idea? Were you sitting in the bath and did it just spontaneously arise? Were you at a conference? Were you listening to other people's talks? All of these things are absolutely fine, but I think it's worth a few moments thinking as individuals how it is we set about creating. And so I'm going to say a few words now about creativity, the art of science. I have used the word art and science in the same clause deliberately. And I should say, in the best traditions of academic plagiarism, that the ideas that I'm going to put forward here were introduced to me by someone called Dennis Sherwood a number of years ago. And they were true then, and I still think they're true now. And to get us into the spirit, I've got a Christmas party game that I'm hoping that everyone is going to play. And I'm hoping that I can persuade people to play and that I can get people to type things into the chat box. And I would urge you to do so in a way that is not just so the panelists can read, but so the panelists and attendees can read. I want everyone to share some ideas around a particular problem. And I want you to share by typing into the typing your ideas into the chat box. So there's 61 of you. I'm expecting to see at least 15 ideas, ideally more than that. So I have in front of me here a piece of paper. I have on this piece of paper 9 dots, and I'm going to pose you a challenge, and I want you to type in the box how you're going to solve the challenge. This is challenge-led research. How can we draw a straight line that goes through all 9 dots? That's the challenge. And I'm going to set my little watch now on my phone, and I'm going to give people 30 seconds thinking time. And then I see someone's already typed something in. Excellent. Okay, just go for it. Just start typing stuff in now. Try not to read them until you've typed your own thing in. Keep going, keep going. There's 1, 2, 3, 4, 5, 6 ideas so far. 7 ideas. I'm going to type one in. Come on, let's have a few more. Two more, and then we'll move on to the next slide. Want to take questions in the meantime? No. My goodness. Assume unstable dots are present between each major dot, in which case we don't have to draw a line at all. First fold horizontally, then vertically. Right. Okay. Now, I'd like to reflect on some of the things that people have said here. And so there is a category of answers which involve doing something with the pen. We're going to make it a large pen, a paintbrush, and we go splash, and we just draw one straight line through everything. There's then categories of answers which involve folding the paper, and then there's different answers there where they've got different folding strategies. Incidentally, normally I see someone tears the paper into 3 strips and then connects the 3 strips end to end, so the 9 dots form a perfectly straight line which you then draw a line through. So there's no tearing the paper written down, but normally I see that one. There's one I wrote down there about standing a long way away, so the resolution limit blurs all the spots together. Sometimes you see people write down, put the paper in some water so the ink runs and the dots all merge into one, and then you can do it. Spiral line. Yes, people then start playing with language, drawing a spiral line, or taking the paper and wrapping it around a cylinder, or putting it on a flatbed scanner. So you move the pen in the X direction, and the paper, you do it sort of diagonally slightly, you know what I mean, and you move the paper backwards and forwards, so the pen goes in a straight line, but the mark it leaves on the line on the paper zigzags. That's another sort of category of answer. And the point of it is, the point which I hope I was trying to make, is that the collection of ideas spans a much bigger creativity space than any one person's ideas did. So maybe somebody had 2 ideas or 3 ideas, but they didn't have 6 ideas. And then the other mistake that we make is, as soon as you've thought about folding, let's say, it's impossible to move away from folding, and what you end up doing is thinking about different ways of folding it. The ideas become derivative. And what I want to do is introduce an idea to you all, that write a paper, get the authors together, and then write down on a piece of paper, don't tell anybody, how could the paper be different? And everybody write down some ideas and then you share them. And there's one way forward whereby you can derive your future papers from your past papers, so to speak, by collecting ideas around how might it be different. The write and share technique. Now let's keep going. So these are the various things that I mentioned that people, I was guessing. Nobody said it's cheating, although normally some people do that, or maybe they just don't engage, and that's the cheating thing. Use a special pen, fold and tear the paper, move the paper while drawing, redefine language, single, straight, through, make the spots larger. Another good one here for physicists, run past it very quickly, so length contraction means all the spots crunch up into one straight line. And the point I was trying to make is, collectively, we said more types and more solutions than any of us thought of individuals. That's a hypothesis. Each type spawns sub-ideas, but if we discuss the sub-ideas too soon, it's hard to get out of the hole and get into different types. Now, I'm going to move over this one here. I want to talk about something else, if I may. I want to deconstruct creativity. So again, this is an exercise I did with Dennis, where we were invited to come along with a paper that was written by somebody else that we really loved, that we wish we'd written ourselves. So the classic paper in your field, whatever that paper might be, and you take a look at it and you go, that was a creative paper. And I should say that the whole premise of this is that whether you do pure research, discovery research, mission-led research, challenge-led research, applied research, commercial development, probably what we respect in all of this and admire in each other's work is the creativity of the new idea. That I'd not seen that done before. That was really clever. That was really smart. So we're going to take one of these papers that has a new idea in it and deconstruct it. Because papers, by and large, have references within them. And on the shoulders of giants and all of that, papers are usually the fusion of several known ideas. And rather than the component being new, it's the way in which those ideas were brought together that was new. And so the paper I turned up with to this event was a paper written by Anton Zeilinger. As it happens, it came out it was a Nature paper. I'd been working in orbital angular momentum for, at that point, probably over a decade. And then Anton published this paper called Entanglement of Orbital Angular Momentum States for Photons. And you go, gosh, I wish I'd written that. And so let's take it apart. And I hope I can take it apart without relying on anyone knowing what orbital angular momentum is. I'll say a few words about it in a second, or indeed other language I'm going to refer to. So we're familiar with the idea that light can carry a spin angular momentum, and we associate that with the polarization of individual photons. It can also carry an orbital angular momentum. If it couldn't carry an orbital angular momentum, we'd never have quadrupole transitions. And that is not associated with polarization. It's associated with the phase structure of the light beam. And the thing that makes it interesting, or one of the things that makes it interesting, is unlike polarization, which has only two orthogonal states, the orbital angular momentum can have any number of orthogonal states. And so from a quantum point of view, if I just use polarization, my photons can be a 1 or a 0. I can transmit a binary code. But if I use the orbital angular momentum, then I can use a much bigger alphabet. I could have 26 different states, and every single photon could be a letter in the alphabet. So it was a great paper. However you want to look at it, you can look at its metrics of citations or just the number of research groups it's inspired. And you look at it, and you look at it again, and you go, well, actually, all he did, I don't mean this in a disrespectful way, is he took the forked holograms of Marat-Soskin. So Marat-Soskin had been using diffraction gratings with a fork in them in order to both generate and measure orbital angular momentum states. He took some work from our own group on orbital angular momentum in Chi2 nonlinear interactions. He combined it with his own world-leading expertise in entanglements and mixed it all together and obtained a brilliant paper. And fantastic. And I think that is probably true of most great papers. I think it's true of most fellowship applications that I see when people start their careers. I think it's true most large grants, that what the idea is you take something that's known, combine it with something else that's known, and then importantly, mix in something in which you are yourself the world expert in. So it's not just a question of going, stem cells are exciting, machine learning is exciting, and nanotechnology is exciting. And what I'm going to do is conceptualize a project which involves stem cells and nanotechnology and machine learning. I'm going to have all these buzz lines in it. It's a guaranteed fundable idea. Other than there's none of me in it. I know nothing about any of those three areas. And therefore, there's no reason really why I'm the right person to do it. And so that why you question requires you to know something, combine it with what others know. And as I've said here, learning through collaboration. Don't sit down and think you can teach yourself. Sometimes you can. Far better to make friends with somebody that knows what you want to know and do something jointly with them. But this idea of known A, known B plus unique U creates novelty. The question then is, novelty is easy, but it might not be useful or interesting. And so every time you come up with creating novelty, you then have to go through a little loop that says, well, was that novelty worth having? Does anyone care? Will it actually solve any problem? Is it interesting? And most times that combination is novel but not interesting. Sometimes the combination is novel and interesting. So let's reconstruct that for a moment and say, what is the skill that you have? You know a lot about photonic crystals, maybe. You're the world authority in photonic crystals. What unique capability do you have access to? I've got an E-beam writer with the biggest field of view in the world. I've got the only UK source of a particular material. What is your uniqueness? And then the question comes, I could just write a paper about, I've used photonic crystals just as an example. Or I could think about how that photonic crystal problem or opportunity might combine with something else. How can I use photonic crystals in gas detection? Maybe I can use slow light. Maybe I can increase the absorptivity of the gaseous transition if I infuse my gas into the photonic crystal. Maybe I should work with someone that understands about gas detection, or maybe I should work with an end user that wants to do gas detection. Where is it that 2 + 2 = 5? Now, if I do that to my own papers, on the one hand, we've talked about orbital angular momentum on the left-hand side. On the other hand, we've talked about optical tweezers. I've got single pixel cameras at the bottom, our working quantum optics on the right. It looks varied, it looks diverse, it looks like I can't make my mind up what I want to do, perhaps, or maybe it looks like I'm highly creative. But actually, all of these have something in common, and that is it's about shaping light beams. So actually, the only thing I know how to do is shape light beams. And I've used shaped light beams in optical tweezers. I've used shaped light beams to explore angular momentum. I've used shaped light beams in imaging, etc., etc., etc. And if one looks at, I just sort of picked out some papers. These are some papers of mine which are reasonably cited, just to pick out some. And you see that all of them, although they're sort of different, actually they're all the same. They all involve shaping light beams. And so in terms of my own creativity, if you want to say that, or the creativity of my group, common to all of this has been, I want to make sure that we are the best in the world at something. And then I'm going to partner with others in using our, let's say, technical skill together with their sector knowledge, application knowledge, knowledge of another area, to do something together that neither of us could do separately from each other. And if I come back to where this presentation started, I started by talking about the work with Thomas Shishmar. I knew nothing about endoscopy. I knew a little bit about endoscopy as it happened, but certainly nothing about single fiber endoscopy. But what we did know about was high-speed beam shaping. And somebody asked me in one of the questions, what sets the frame rate? Well, what sets the frame rate is the speed at which you can reshape the beam. And so beforehand, Thomas was reshaping his beam about 60 times a second. And then when we got together and started using the digital micromirrors, we were able to do that 20,000 times a second. So the frame rate went up by almost a factor of 1,000. Now, and we, on the other hand, I knew nothing about transmission matrices, and we learned all of that from Thomas. When I got into quantum optics with Bob Boyd, I knew nothing about quantum optics. Bob Boyd knew nothing about spatial light modulators. We met each other at an editor's board of a journal and decided we'd like to learn what the other person knew. And so two of our group, Jonathan Leach in my case, and Anand Yar in his case, got together. We taught him to use spatial light modulators, and he taught us how to do entanglement experiments in quantum optics. And we published, I don't know, 20, 30 papers together, exploiting basically that idea. So the future, I said I wasn't going to do it, and now I've fallen into my own trap. So the title of these things were hopes. Optics, photonics, and emerging technologies. And so I thought I would write down one thing under each of them. And I'm going to suggest to you that a future, just one future, maybe there's many futures, but a future will be combining something from each of those areas. And so what have I written down? I've written down in optics, I've written down imaging without images. What did I mean by that? I mean, for hundreds of years, people have made lenses. And the sole purpose of a lens is to form an image of the world on top of a film or sensor. And I'm going to say, sod the lens. We don't want a lens. We'll just have a multi-pixel detector. I'll just record whatever it is that comes in, and I'll fix it all on my computer afterwards with a transmission matrix. And I will essentially computational imaging. So I do not need to form an image. Photonics. I've taken a very technical view of photonics. A lot of our experiments in quantum optics have been enabled thanks to the wonderfully clever people at E2V that made EMCCD chips that could have single photon sensitivity in an array format. And I think there's a lot of mileage still. There will be a lot of mileage to be had of emerging detector technologies, which you won't have to do, you just have to buy them. And that might be SPAD arrays that do photon timing. It might be arrays that will do photon number resolving. It might be arrays which do true single photon detectivity with no noise. I think the technology for multi-pixelated photon detection, both in the visible and in the invisible wavelengths, is going to change dramatically over the next 5–10 years. How would it be different? How would your experiment be different if your camera was 10 times better than it was? Just ask yourself that question. And if the answer is it would be very different, get talking to the Hamamatsus and the Andors and the E2Vs of this world and see what's around the corner. And then, of course, no grant application would be complete without the magical words machine learning. it's a must in everything that you do. But it's also serious in that when I started my PhD, my BBC B micro took 5 minutes to Fourier transform an array of 512 elements. Wow. Now I can Fourier transform 1 million pixels in a couple of milliseconds. Computing technology has changed dramatically. And that means all the kind of algorithms that used to exist that you would never dream of using, you can now run on your phone. And that is not just about coming back to where we started with the optics without imaging, the diagonalization of the large matrices to compensate for the transmission matrix. Even then, I've assumed that I'm somehow converting this mess of signal into an image. Actually, I'm not interested in the image, I'm interested in a decision. Why don't I just cut out the middle person and move straight from the data to hit the brakes or dodge, duck, cover, whatever the decision is that you are going to think about doing, operate, don't operate. Why bother with the intervening image? And so I think that is an exciting blend mix of the three. So that is the end of my slides. Work with the smartest people you can find that want to work with you. And you can learn something from each other. And, work somewhere you're going to be happy. If you're miserable and don't like the people, you're not going to have a great time. So I think the people you work with are probably more important than what you're working on. How about that?